Hello everybody and welcome to chapter 5.2 of Advanced Functions. Today we'll be discussing the graphs of reciprocal trigonometric functions. So again, we're going to be following the same procedure as last time when we were learning how to graph the primary trigonometric functions. So at first I divided it into two parts. So we're first of all going to be learning how to graph the secant and the cosecant graphs. Then we're going to learn how to graph the cotangent graph. And lastly, we're going to discuss the difference between reciprocal trigonometric functions and the inverse trigonometric functions. Okay, so let's get started. The graphs, the secant and cosecant. Now that we've learned how to graph the trigonometric functions, we have to learn how to graph the reciprocals. Their graphs are closely related to one another, which makes sense. So immediately what we have to know is that the graphs of y equals to secant of x and y is equals to cosecant of x are periodic, just like the primary trigonometric functions of cos of x and sine of x. So the graphs of y is equals to cosecant of x and y is equals to secant of x are similar in shape and have a period of 2 pi or 360 degrees, and they have no amplitude. That might come a little bit like a surprise since the sine and cosine graphs did have an amplitude. However, don't worry about it, we'll discuss why this is the case. So at first, you can easily graph these functions by using their respective primary trigonometric functions. So we know that the reciprocal functions are equal to 1 over the primary trigonometric function that we're working with. So secant of x is equals to 1 over cos of x. So with that, we also know that all the old zeros in our primary trigonometric function are now going to become asymptotes, since now those zeros are in the denominator. So what else we know is that all the old maximum points will now become the local minimum point, and vice versa. So all the old minimum points will now become the local maximum points. So in case you're wondering what this is, I will now show it to you. So on the right and left of the point, let's for example select the point 1 at pi over 2 for the graph of sine of x, right? At this point, we could now go to the left and or right. If we were to go to the left of the function, we are actually going to be approaching positive infinity or negative infinity, depending if the original point was a maximum or minimum, respectively. Okay, that might sound a little bit confusing still. Well, let's think about what happens when we go to the left of the point 1. So we're going to 0.9, right? So we'll be dividing 1 by 0.9, which should give us a value that was greater than 1. If we're going to go down even more to the left, we're going to eventually approach 0, right? If it is approaching 0, that means we're dividing by a really, really small number, which should give us a really large number, which would mean we're approaching positive infinity. The reason why I'm saying that it depends on the original point, so for example, if we had a maximum that was above the x-axis, to the left of that and to the right of that, we're going to approach positive infinity. However, if we were talking about a minimum point that was below the x-axis, we're going to be dividing by a very small negative number, which would mean that we're approaching negative infinity. I'll show you how to graph these functions in a moment. Okay, so let's get started. Up first, let's try to graph the function of y is equals to cosecant of x. What we know for sure is that cosecant of x is the same as 1 over sine of x, right? So, since this is our first time graphing this function, let's actually graph sine of x. Well, by now, if you did the practice, you should know where the zeros are, where the maximum and minimums are. So our graph will look something along the lines of this. And then we would have the same thing on this side. However, I trimmed just a little bit since we don't need to graph two periods of the same function. Now, let's talk about what we've discussed. Well, we know that the old zeros will now become asymptotes. So let's jot them down. This is x is equals to 0. This is x equals to pi. And then we have 2 pi. Sorry, that wasn't straight. And this is x equals to 2 pi. And then our last one is at negative pi. Now, with this information, let's talk about what we've discussed on the slides. Well, we know that we had 1 as our local maximum, right? And then we said that we will now be approaching positive infinity from the left and right. So this is the kind of shape it would have, right? Then for our local minimum, we would approach negative infinity. So let's draw the shapes. This is what our second branch would look like. So for here, we should also have a negative branch. This shape over here is actually our graph of y is equals to cosecant of x. As you can see, it's extremely simple. You just need to understand the behavior of both the branches at the asymptote. But again, it's nothing difficult because they're just approaching 0, which means they're dividing by a very small number, which would in turn make this number very, very big. However, since this value was negative, this has to be negative as well. That's all that we are doing. So now let's look at the graph of secant of x. Okay, so now let's talk about the graph of y is equals to secant of x. Again, secant means 1 over cos of x. We could graph our cos chart, but I don't think it's necessary since we just learned how to do that with our sine. So all we have to really do is remember where our key points were. So our key points were 1, then over here, then -1, then 0, then 1. Over here, we would have had a 0 and then -1, right? Now, from these points, we know that wherever we had a 0, we should have a vertical asymptote. So let's show the vertical asymptotes. Now we've done that. From the local maximums, we should be going up. Wait, I'm going to change the color. Let's go for black. So from the local maximums, we should be going to positive infinity. From our local minimums, we should be going to negative infinity. So over here, we could just draw half the branch, so we know it's continuing. And over here, we could actually draw half of the negative branch, since we know it's still continuing. This is the graph of secant of x. As you can see, all of these graphs are super simple to do and like extremely fast. That is what makes them so much fun to do. You don't have to focus on making them as detailed as possible. However, you should definitely still have a smooth curve, no pointies, like that's not allowed. You should always label your asymptotes. So this is x is equals to pi over 2, 3 pi over 2, negative pi over 2. You don't have to label the vertexes unless specified, so make sure you talk to your teacher about it. Lastly, you should always label your diagrams or your graphs on the actual chart. paper or graph paper, whatever you're given. With that being done, we can now move on to the graph of cotangent. Personally, cotangent is a very special graph for me just because it's super simple once you actually see the graph, but analyzing it before that point might seem a little bit tricky. However, we're still going to go over how to do that. So immediately what you have to know is that the graph of y is equals to cotangent of x is periodic, just like every other function we've been working with in this unit. We also know that the graph of y equals of tan x is the graph of sine of x over cos of x. So the graph of y equals to the cotangent of x is the reciprocal of the tan of x graph, which would mean it actually equals to cos of x over sine of x. This lets us use the exact same process that we use to analyze the graph of tan. So let's do that. Immediately we know that there will be asymptotes whenever the denominator is equals to 0, and the denominator is equals to 0 when sine of x is equals to 0. And since we already know how to graph sine of x, we've learned the unit circle numerous times, we know that sine of x equals to 0 for every multiple of pi. So like 0, pi, 2 pi, negative 7 pi, negative billion pi will always be a 0. So those will actually be our new asymptotes. We also know that the values of x, where cos of x is equals to 0, will become our new x-intercepts. So again, we could talk about the cosine graph. We should know where that graph is equals to 0, and that is whenever we have a multiple of pi over 2. So again, we have now found the zeros, or the x-intercepts, at every multiple of pi over 2. With this information, we just have to analyze the behavior of the graph as it approaches the asymptotes from the left and from the right. Luckily for us, we have the x-intercepts to help us out. So let's first talk about how the graph behaves to the left of the function, or to the left of the asymptote. Let's take the point x is equals to negative pi over 4, because again, that's a special angle. It should be really easy to work with. We know that pi over 4, like tan pi over 4, is 1, and since 1 over 1 is still 1, we know that cotangent of pi over 4 is equals to 1. Now that we have negative pi over 4, we know that the answer should be negative, and so we get negative 1 as our point. So we have the point negative pi over 4 and negative 1. We know that the value of pi over 2, or negative pi over 2, is 0, which means as we were approaching the asymptote from the left, right? So we went from pi over 2 to pi over 4, our value started to decrease. We were going from 0 now to negative 1. Since the values are decreasing when we're approaching the asymptote from the left, we could safely assume that it's going to increase to negative infinity as we are approaching the asymptote. Using this exact same logic, we could find the behavior of this graph to the right of the asymptote. So again, let's talk about x is equals to pi over 4. That will get us a value of 1. We know that pi over 2 is 0. So now we went from 0 to 1, which means we're increasing. Since we're increasing, we're going to increase all the way to positive infinity, and thus we have found out that from the right of the asymptote, the graph is increasing to positive infinity. Now we could safely graph our function. Okay, so let's now graph the function of y is equals to cotangent of x. Again, we have learned that our asymptotes would be wherever sine of x is equals to 0, which is on every multiple of pi. So let's draw them out. There you go. Then we also know for every point where sine or cos of x is equals to 0, we would have a 0. So this is a 0, this is a 0, this is a 0. Now that we talked about how the graph behaves to the left and right of the asymptote, let's select one of the asymptotes. For example, this one. We said when it's approaching from the left, so from here, it is going to negative infinity. Then we said from the right, it is approaching positive infinity. Okay, that looks good. Now let's continue. Negative infinity, positive infinity. Negative infinity, positive infinity. And again here, positive infinity. So we get these S shapes for the graph of cotangent of x. And it's actually really similar to the graph of tan of x, but I don't want to confuse you, which is why I'm not going to show you it. So again, just know your key points for sine of x, cos of x, and how it behaves in the asymptotes. And you'll be more than fine for graphing this function. Now here is the graphs using Desmos, just so you could see them in a better light with proper, not shaky hands. As you can see, the graph of secant and cosecant are actually really similar. The reason why they're really similar again is because they are coming from the sine and cosine function, and those functions we've already discussed are or could be transformed into one another using translation. So the same thing goes for here. We could actually move this graph over by pi over 2 to the left, and we would get the same function, or we could use this graph and move it pi over 2 to the right and get this function over here. Lastly, this is our graph for cotangent of x. I've also marked all the asymptotes. As you can see, we get our zeros in the same place as our cosine, and our asymptotes are in the place where sine equals to 0. With that being said, we could now move on to the last part of this chapter, which is differentiating between reciprocal trig functions and the inverse trig functions. Well, one important thing that you must learn and must understand is what the difference between the two is. We know that the reciprocal trigonometric functions are secant of x, cosecant of x, and cotangent of x, while the inverse trigonometric functions, or the expressions, are sine to the power of -1. I know that's not how you say it. You say sine inverse of x, cosine inverse of x, and tan inverse of x are, again, the inverse trigonometric expressions. Now, all of these have different meanings, and this is what they actually mean. Secant or cosecant of x means 1 over sine of x, while sine inverse of x is actually asking you a question which makes you find an angle that has the sine ratio equal to x. So for example, if you were told to find what sine inverse of 1 over 2 is, you're trying to find the x value where sine of x is equals to 1 over 2. Again, this kind of idea follows for all the other functions and inverse functions. So secant of x means 1 over cosine of x, while cosine inverse of x asks you to find the angle that has a cosine. Sorry, I forgot to change that. Cosine ratio equal to x, and this should be a tangent ratio of x %. There you go. Again, the last one would be cotangent of x means 1 over tan of x, while tan inverse of x asks you to find an angle that has a tangent ratio equal to x. It is also really important for you to understand that the values of the reciprocal trigonometric ratios can only have one possible answer, as we are dealing with a specified radian angle. So if we're talking about cotangent of pi over 4, it has to be one specific answer, because pi over 4 is our exact point on the graph, and that exact point will only have one y value, since that is the definition of a function. However, the inverse of trigonometric expressions can have infinite answers, as again we're dealing with we're trying to find the angle that has the same ratio that equals to x, which means if we were trying to find a point or an angle where sine is equals to 1 over 2, since the function is periodic, we would be repeating this value every 2 pi. That is why we could technically have infinite answers for this question. Now, with that being said, this is the homework for today. A lot of it is actually word problems, but they're not difficult word problems. So let's show you some of them. For example, there you go, 9. We have a lifeguard at position L spots a swimmer in trouble at one corner of the pool. Oh no. S is what the angle is called, or the corner. She runs down the length of the pool to position P and then dives in to swim the distance D from P to S, and then they did this wonderful diagram. So we need to show that the relationship, or that the swimming distance is given by the relation D is equals to W secant of X. So again, you just need to understand what secant means, which is 1 over cos, which cos means adjacent over hypotenuse. So secant is hypotenuse over adjacent, right? And that is all you have to do. If then it's asking you how to, if L is equals to 2W, determine the range of values that X may take on, given that P can be anywhere along the side of the pool. So now you're just talking about the restrictions on this variable. Again, you could just analyze the graph of what this could possibly mean. Then it's asking you to find the range of D's, or distance that the value could take on. So that is our y value. Lastly, it's asking you, for D, it's asking you to sketch the graph over an appropriate interval, which is what you just found out from B and C. Lastly, it's asking you to suggest reasons why the lifeguard might choose to swim rather than run down the length and width to reach the swimmer. So what that would mean is just critical thinking, just why might someone choose to do that? It might have to do with the distance, it might have to do with speed. It's whatever you think it might be the answer. These kind of questions are similar throughout. It's just trying to get you to analyze what each of the reverse trigonometric functions mean and how they apply to the real world. Most of the time it's going to be talking about the fact that it's like inverse of the primary functions, which is easier to understand in these kind of contexts. So yes, that is around it for the homework. If you have any questions, feel free to contact me. Again, if you just know how to analyze the functions and understand how the functions are derived, you shouldn't have any problem with it. But if you do, just email me, add a comment, message me on Instagram, whatever you want, whatever you feel like is the more important or easiest thing for you to do. With that being said, I hope you have learned a lot from this class or this lesson today. It was probably a bit on the shorter side, but tomorrow we're going to be talking about the transformations of sine and cosine functions, which should always be a lot of fun. So yeah, thank you for listening. I hope you had a wonderful time, and I can't wait to see you next time. Bye bye!